The main part of this segment is going to be Hooke's law, but before we can really look at that, I'm going to introduce periodic motion. Periodic motion describes objects that swing back and forth along the same path. So if you visualize a pendulum, like I've drawn here on the left, or a swing, you can see that these two objects pass back and forth through the same path, following the same pattern over and over again. The same is true for a mass on a spring, as I've drawn on the far right. This mass will move back and forth based on the force of the spring. That's what Hooke's law is really going to lead us to study. Here are some basics for spring motion. A spring is at equilibrium point, as I've drawn here, when it's at its relaxed length, or the length it would have naturally without any external forces. When a mass is on the spring and it reaches equilibrium point, the velocity reaches its maximum. However, because the spring is at a relaxed point, it exerts no force, so we say F is 0, and therefore acceleration is also 0. There are two other extreme positions on the spring that the mass can occupy. The first is the maximum compression. This is when the spring is as far condensed or compressed as it's going to be within the mass's pattern of motion. The other is the maximum stretch. This is when the spring has been stretched as far as it can possibly go, and the mass is about to be released from that stretch point. At these positions, the velocity is 0. However, because the spring is under so much stress, the force is at a maximum, and therefore the mass's acceleration also reaches a maximum. And it's important to note that in the real world, a spring set in motion in this way would eventually slow and then stop because of friction. But in the situations we're studying, we're going to make sort of ideal situations in which it oscillates indefinitely, and we can study the motion of the mass. So with this information in mind about springs, this is Hooke's law. It states that F, or the elastic force of the spring, will be equal to negative kx. Now we can look more closely at what these variables mean. The negative sign suggests that F, so the force, and x, the displacement, have opposite directions. So you just need that to switch the directions of the two. The spring constant is something we've gone over before when we were studying work and energy. It's measured in newtons per meter, and it's basically how much force is required to stretch the spring a certain distance. Finally, we have x, which is the displacement. This is the distance of the mass from the spring's equilibrium point, or its relaxed position. And just to note, when a mass is on a spring, this entire system becomes an example of simple harmonic motion. Simple harmonic motion is defined as periodic motion as a result of a restoring force that is proportional to displacement. So as you can see, that makes sense because here we have a force and a displacement that are proportional to one another. And in this case, the elastic potential of the stretched or compressed spring will provide that restoring force that it needs for the motion. The concept of periodic motion can also be implied when we're looking at a simple pendulum. This also has periodic motion, just like the mass on the spring, because the pendulum is moving back and forth on the same path. However, in this case, the restoring force comes from gravitational potential. In other words, it's a component of the bob's weight. As you can see over on the left, I've drawn this pendulum with a bob on a string, and we have these two forces on a bob. We have mg, or the force of gravity, the bob's weight, and then we have tension, which is pulling up on the string. Now, if I were to draw the two components of the bob's weight using these axes, as you can see, there's this x component that would point in and kind of pull the pendulum along its path of motion. That's the restoring force that keeps it in simple harmonic motion. You might wonder what happens to the pendulum when it reaches this lowest point. At this point, the gravitational potential is all pointed downward because that's the only component of the pendulum's gravity. However, in this case, momentum is what keeps the pendulum moving. You'll remember from previous chapters that momentum must always be conserved. So in this case, because the pendulum starts off with initial momentum, it has to keep moving even through its lowest point. So here are some practice problems for section 11.1. Number 1. A slingshot consists of two rubber bands. If it takes 32 newtons of force to stretch the bands 1.2 centimeters, what is the spring constant of the bands? So in this case, we're looking for K, which we know is measured in newtons per meter. So we basically want to find how much force is required to stretch the bands 1 meter. We have 1.2 centimeters and 32 newtons, so we'll put the newtons on top, that's 32, and then 1.2 centimeters needs to be converted to meters, that's 0.012 meters. If we do this division, we get that K is equal to about 2,667 newtons per meter. That's how much force is required to stretch the rubber bands. Number 2. How much force is required to pull a spring 3 centimeters from its equilibrium position if the spring constant is 2,700 newtons per meter? So now we're starting to use Hooke's law. We see force is equal to negative kx, and then since this problem is just asking how much force, or the magnitude of the force, we can sort of disregard this negative sign because we're just looking for magnitude rather than magnitude and direction. So with that in mind, we're looking for force. We have k, which is 2,700, and then we have 3 centimeters. That would be 0.03 meters. I multiply these together and get 81 newtons of force. In this section, we're going to start to look at waves, and in order to do so, I'm going to define some basic terms that will help us to study these waves. So the amplitude is defined as the maximum displacement from equilibrium position. I'll refer to this in the future probably as A. So the amplitude would be this distance. You may recognize this from math if you've had sine or cosine waves before. The amplitude is simply this distance from the equilibrium point to the farthest point away. The period is the time it takes for a complete cycle to occur. So a complete cycle for this wave would be from this point to this point. That's where the wave completes one full pattern of sort of this S shape before repeating and forming more S shapes later on. Whatever time it takes for this to occur is expressed as t, that's the period. Finally, the frequency, which is written as f, lowercase f, is the number of cycles per unit of time. So this is the inverse of period, which we also call 1 over t. And frequency is expressed with the unit hertz, which is written as Hz. So that'll be used later on as well. Going back to the simple pendulum we discussed in chapter 11.1, I'm going to give you an equation for the period of a pendulum. This depends on the length of the pendulum and the free fall acceleration, and it's simply the time that it takes for the period to complete one complete cycle. And these are different factors than the factors that influence the period of a mass on a spring, which we'll get to later. So we write the period of a pendulum as t, or period, equals 2 pi root L over g, where L is the length of the pendulum from the top to the bob, so it's this length, and g is gravitational acceleration, which we know to be about 9.81 meters per second squared. So when we're applying this equation, you can visualize that as the length of the pendulum increases, its period would also become larger because it has a longer arc to travel through. If I draw two pendulums where one is very short and one is longer, and you visualize these pendulums swinging back and forth over the same angle, the longer pendulum at the bottom would have a much longer arc to travel through than the smaller one. You may also wonder why factors such as the release angle are irrelevant when we're measuring the period of the pendulum. Well, it's somewhat irrelevant over small angles because the initial acceleration is greater if you release the pendulum from a bigger angle, and that will cancel out the fact that a pendulum released from a bigger angle has a longer distance to travel through. The equation for the period of a spring looks somewhat similar to that of the pendulum. However, it depends on slightly different factors. In this case, we write that the period, t, is equal to 2 pi root m over k, rather than L over g. So this m is just the mass of whatever block or object you have on the end of the spring mass, and k is the spring constant. This equation is also pretty logical because you can visualize that a mass that's larger will take longer to complete the same cycle because force is mass times acceleration, and as the mass increases with a constant force, the acceleration would have to decrease, making it take longer. The period of the mass on a spring is inversely proportional to k, or the spring constant, because as that increases, the spring will exert a greater force on the mass, making the period shorter and the motion faster. So here are some practice problems for section 11.2. Number 1. You are designing a pendulum to have a period of 1 second. How long should the pendulum be? So we know that pendulum period depends on length, so I'll write out our equation where period is equal to 2 pi root L over g. Now we're ready to plug in some variables and solve. So we know that we want the period to be 1 second. That will be equal to 2 pi root L is what we're solving for, and then G we'll call 10, just to make it a little bit more simple. Now to isolate the L, I'm going to divide both sides by 2 pi, and I get that 0.16 is equal to L over 10, and that's still the square root, sorry about that. So then I'll square both sides to get rid of that square root, and I'm left with 0.025 equals L over 10. Now, just by multiplying this 10 over to the other side, I get that L is equal to 0.25 meters, or in other words, L equals 25 centimeters. That would be the length of the pendulum. Practice number 2. Calculate the period of a 3.5 meter pendulum in the following locations. A, the North Pole, where G is equal to about 9.832 meters per second squared. Okay, so in this case, they're changing the variable of free fall acceleration, or G, which is slightly different at different locations on Earth. And we're solving for the period. So we have our same equation where T is equal to 2 pi root L over G. So for the North Pole, T equals 2 pi times the square root of 3.5, that's the length of the pendulum, over 9.832. That's the value of G. Now if I plug in all these values and solve, I get that the period is about 3.75 seconds. That's how long it takes for the pendulum to complete one cycle. Now they're asking for Indonesia, which is closer to the equator. In Indonesia, G is about 9.782 meters per second squared. So again, I'm going to be solving for period, so I'll do 2 pi root L over G. T equals 2 pi, and then I'll plug in my variables where L is still 3.5 and G is 9.782 meters per second squared. If I simplify and solve this, there's not actually much of a difference. I get 3.76 seconds. So that's how long it would take for the same pendulum to complete a cycle in Indonesia. Number 3. A mass of 0.3 kilograms is attached to a spring and set into a vibration with a period of 0.24 seconds. What is the spring constant? So now we're looking at a situation with a spring, which means that we'll be using a slightly different equation for its period, where T equals 2 pi times the square root of m over k, or mass over spring constant. Now we can plug in all the variables they've given us. The period is equal to 0.24 seconds. Then we have 2 pi root 0.3 over, and then k is what we're solving for. So I'll divide both sides by 2 pi, and I find that 0.04 is equal to the square root of 0.3 over k. Then I'll square both sides to get rid of the square root sign, and I'm left with 0.001 equals 0.3 over k. If I multiply the k over here, I would have 0.001k equals 0.3, so then I'll divide both sides by 0.001 to isolate the k. I get that k is equal to about 205.6 newtons per meter, and that's the spring constant for this spring. Finally, we have number 4. A 0.75 kilogram mass is attached to a vertical spring and stretches at 0.3 meters. A, what is the spring constant? Okay, so we know that k is measured in newtons per meter. We know that the spring was stretched by a 0.75 kilogram mass. So that would be 7.5 newtons. And then meters, we have 0.3. That's how far it stretches. Now I'm dividing, and I get that the spring constant is about 25 newtons per meter. In part B, it says that the system is now placed on a horizontal surface and set vibrating. So basically, if you can visualize this, the spring is now placed like this, and the mass is allowed to oscillate back and forth. It's asking what is the period. So T is equal to 2 pi times the square root of m over k, and we solved for all these variables now, so I can plug in 2 pi square root of 0.75, which is the mass, divided by 25, which I just solved for in part A, that's the k value. And then by simplifying, I get that the period is equal to 1.1 seconds. Wave motion results from several recognizable everyday situations. A key example is that of a rock being dropped in water. You can probably imagine the ripples that would result from this motion. In this case, water is the medium through which the waves travel. In other words, it's a physical environment where this disturbance takes place. That makes these waves mechanical. A mechanical wave is defined as a wave that requires a material medium through which to travel, so in this case, water. Now we'll take a look at some ways in which these waves can be applied. So a pulse wave is defined as a wave that consists of a single traveling movement, or pulse. So in this example, a person's hand causes this pulse within a rope that's attached to the wall, and that creates a wave that moves towards the wall. This produces simple harmonic motion, like we've discussed in the past, that can be modeled through a sine wave if we were to study this further and do calculations. Let's take a look at some types of pulse waves. The first type of wave that we're going to be studying is a transverse wave. This is a wave that vibrates perpendicularly to the direction in which it's traveling. So if we're taking this rope against the wall example, we see that the rope now has many waves in it. The direction in which it's traveling is this way, horizontally towards the wall. However, the vibrations occur in the vertical direction, in other words, perpendicular to its overall direction of movement. That's what makes the wave transverse. Here are some vocabulary words that will be useful when defining transverse waves. The first is a crest. This is the highest point above an equilibrium position. So in this example wave below, we have crests occurring here and here. Those are the highest points above its sort of neutral position in the middle. The second vocabulary term is the trough. This is the lowest point below a wave's equilibrium position. So troughs occur over here and down here. The amplitude, as I defined previously when we were discussing springs and those waves, is the maximum displacement from equilibrium position. So both crests and troughs form the amplitude, but this is just expressed as the distance away from equilibrium, which is the same in all of these cases. Finally, we have the wavelength, which is defined as the distance that the wave travels during one cycle. In this case, the wavelength would be from this peak to this one. That's one complete cycle. And that's expressed using the variable lambda, which is sort of this little swirly shape that I've drawn for you. So those are the measurements that we'll use most commonly when we're looking at transverse waves. In addition to transverse waves, we have longitudinal waves. These are waves where the particles vibrate parallel to the direction of the wave's motion. So for example, a spring or a slinky. In this case, we have a wave that's traveling in this direction across the spring, and the particles are moving back and forth in a direction that's parallel to this displacement. These waves are also modeled using sine curves, or they can be if we want to do calculations. And a real-life example of a longitudinal wave is a sound wave moving through air. Here are some terms for longitudinal waves. The first is the frequency. This is the number of waves that pass through a given point in a unit of time. So say we're looking at this sort of model wave I've drawn below. This represents coils on a spring that are stretching and then compressing. And we have a point in the middle. Now these particles are going to be constantly moving back and forth through the equilibrium point, or the point I've defined as the center. And the frequency will be described using the number of little waves that pass through the point, so basically the speed of the wave. And then the period is the time for one complete cycle of vibration. So again, these are inverse quantities. When we're looking at the motion of waves, we'll also be modeling wave speed. So we learned from previous chapters that velocity for any moving object is defined as x, or displacement, divided by the time that it takes for that displacement to occur. When we're looking at waves, however, we've learned that the displacement is really lambda, or wavelength, and the time is really the period. That would be how far it travels in a certain time. We also know that frequency is 1 over the period. So we can rewrite this as lambda times 1 over the period, or wavelength times frequency. Therefore, we define the velocity of a wave as wavelength times frequency. That'll be useful in calculations later on. And just a note that the speed or velocity of a mechanical wave is constant for any given medium. So if you have, for example, a wave rippling through water, that wave will be constant if it stays in water. However, it would move at a different speed if it were moving through a different medium, such as air. In some cases, the motion of waves can also cause energy transfer. When energy is transferred, it is proportional to wave amplitude, or specifically the square of the amplitude of the wave. So in this case, we have energy, which I've written as E, and that's proportional to amplitude squared. So if I were to increase the amplitude, making the wave carry more energy, for instance, if I made this 2A, it would be squared, and the energy would increase by a factor of 4. Let's do some practice problems with wave properties. Number 1. A piano emits a frequency of 4200 Hz. What is the wavelength of this sound if the speed of sound in air is 340 meters per second? So I have this equation that I defined before, where velocity of a wave is equal to wavelength times frequency. Now we know that the speed of sound in air is 340 meters per second, so that'll be the velocity. Then the wavelength is what we're solving for, so we'll leave that as lambda, and then the frequency is 4200 Hz. Now if I divide both sides by 4200, I get that wavelength, or lambda, is equal to 0.08 meters, which is 8 centimeters. That's how long the wavelength is. Number 2. If the amplitude of a sound wave is increased by a factor of 4, how does the energy carried by the sound wave in a given time interval change? So we know that energy is proportional to the amplitude squared, and we're increasing the amplitude by a factor of 4. So now we have 4a on this side, and we still have energy. So if I'm squaring the 4a, I end up with 16a squared, meaning that the energy increases by a factor of 16. So you can say that the energy that's produced is 16 times as great. Number 3. A tuning fork produces a sound with a frequency of 256 Hz and a wavelength in air of 1.35 meters. What value does this give for the speed of sound in air? So now we're solving for the speed of sound, so that's v. And then once again, velocity is equal to wavelength times frequency. So I'll leave this variable as v because we don't know its value yet. We know that the wavelength is 1.35 meters, and the frequency is 256 Hz. If I multiply these values together, I get that the velocity of sound in air is about 345.6 meters per second, which is pretty similar to the value they gave us before of 340 meters per second. We know from experience that two physical objects can't occupy the same space at the same time. However, two waves can. You can think of the overlapping sounds of different instruments at a concert as an example of sound waves overlapping. When two waves overlap and combine, it's known as superposition. And when superposition takes place, the waves undergoing superposition interact to form interference patterns. Let's take a look at some applications of this. So there are two different types of interference or superposition that we're going to be looking at. The first is constructive interference. This occurs when individual displacements on the same side of equilibrium are added to form a resultant wave. So as I've drawn here, we have these two waves coming at each other from two different sides of a rope, and they're on the same side of equilibrium. Both are above the equilibrium point, or this bottom point on the string. These two waves would add to form a greater wave, and that's known as the resultant. Conversely, destructive interference is caused when individual displacements on opposite sides of equilibrium are added to form a resultant wave. So in this case, we have one wave that's above the rope and one that's below. And they're sort of effectively subtracted, so this first one goes up, second goes down, and they create this resultant wave. When waves interact with external circumstances, reflection is sometimes caused. There are two different circumstances where reflection can occur. The first is a wave with a free boundary. So as you can see here, I've drawn a rope that has sort of a loop that ties it to a pole at the end. That means that it's free to move up and down along the boundary. When the waves are reflected around a free boundary, they reflect and travel backwards in the same direction. So this wave that came at the wall this way is now traveling back exactly as it came, but in the other direction. The other type of reflection can occur around a fixed boundary. I've taken the same rope, and in this case, the rope is tied to the wall, so it's fixed. Now, if we were to send a wave running down the rope towards the wall, the wave would reflect and reverse. So it would go back in the other direction below the point of equilibrium. The final concept we'll look at in this section about wave interactions is standing waves. These occur when a wave pattern appears to be stationary as a result of two overlapping waves with the same frequency, length, and amplitude in opposite directions. So this is sort of a complicated definition to grasp, but we can look at these standing waves as being sort of a series of nodes and antinodes, which are defined as these small points between sort of lumps of wave, those are nodes, and then antinodes, which are the largest point, or the waves expand to be large. Say this wave occurs in a string that is 8 meters long. Down here, each section would be broken into 4 meters, and then here, broken up again into 8/3 meters. Those would form the standing waves. And a quick note about standing waves is that only the resultant wave pattern is standing, however the original waves are still traveling. So standing waves don't imply that there's no wave movement, only that the resultant waves are fixed as a result of the waves vibrating with the same frequency and wavelength. Here are some practice problems for section 11.4. Number 1. A wave of amplitude 0.3 meters interferes with a second wave of amplitude 0.2 meters. What is the largest resultant displacement that can occur? So we know that we have these two waves. One has an amplitude of 0.3 meters, and the other is slightly smaller. It has an amplitude of 0.2 meters. So the largest resultant displacement would occur if the waves came at each other in a situation of constructive interference. So their two amplitudes are added to form this greater final amplitude. That would make the largest resultant displacement 0.2 meters plus 0.3 meters, which would be 0.5 meters. Number 2. Which of the following wavelengths will produce standing waves on a string that is 3.5 meters long? So we have this string, it's 3.5 meters, and it's vibrating to produce standing waves. So we know about standing waves that they form sort of a series of nodes and antinodes, and that those have to be evenly divisible into the length of the string so that it can form equal segments, although this is not exactly drawn to scale. So the first is 1.75 meters, and by the way, more than one of these answers can be correct. So 1.75 goes into 3.5 twice, which means that this cycle would form a pattern sort of like this, with two parts to it. So that would work to form a standing wave. The second, 3.5 meters, that would just form one big arc. That would also work. That's also evenly divisible into 3.5. 5 meters is not evenly divisible into 3.5, so that would not work. And then finally, 7 meters, since 7 is 3.5 times 2, that would also work. So we're left with all of the answers except C. So this has been Chapter 11 of Holt Physics, in which we studied waves and wave interactions, as well as simple harmonic motion. Thank you for watching.